Hi everyone, I'm Philipp. Hey, everybody's still awake? Good. Let's talk a bit about scaling and Elasticsearch and what to do stuff there. So maybe you may remember that logo back a while ago. That was how we got started, and kind of the headline for Elasticsearch still even in the latest version is always the tagline is for search. That's still kind of true because if you search on any of these sites behind the search box, there is Elasticsearch doing the search for you. So that is widely accepted that this is how you do search. Then we added more products to kind of the family. We always say the Elastic family. That is also very widely used. Maybe you know the ELK stack, which is kind of like this funny combination of Elasticsearch, Logstash, Kibana. So you have Elasticsearch which stores the data, Logstash that can get the data, and then Kibana that can visualize the entire thing. And well, that is also very widely used. So if you're using any of these platforms, like I'm using way too much Slack, I have a Fitbit. I don't use Lyft because it's only available in the US, but they log pretty much all the activity, or at least security events, and lots of other interesting things they log with the Elastic Stack. And then kind of the entire thing developed further. We added this new component called Beats, which is like a lightweight agent or shipper. The problem is there is no B in ELK, and then we kind of had to, the ELK had to re-find itself. And then it figured out that maybe it should be this, the BELK or the ELK B, because you can see it has the B body and the ELK horns. However, since we're always about scaling, even marketing figured out that this is not very scalable. Because what happens if we add another open source product? Then we probably have another letter, and then we need to redo the entire marketing and need to redo everything, so it's not very scalable, and we always redoing everything is hard. Also, like, whatever is the next letter, it would be very hard to make up another animal. So we kind of gave up on the animals, and we now just call it the Elastic Stack, because that's super scalable also from the marketing perspective, because whatever open source product you have, you can just put that into that, and we don't have to redo the entire branding, so that's easy. And that's also widely used for metrics, for example. So if you play any online games with Blizzard or Car2Go, I'm not sure how widely used, or if Car2Go is available in Russia, but it's like the car sharing thing that is all over Europe. Or if you buy anything on eBay, they collect a lot of metrics from their containers or their infrastructure in the Elastic Stack as well. So that's for metrics. And then a common question that I see is that people say, like, I'm not going to use a search engine for metrics. This sounds like a really bad idea. Because, well, it's maybe good for search, and maybe I understand that I want to put logs in there because nobody wants to store logs. What you want to do with logs is you want to find the logs and see what is going on in the logs. So maybe search makes sense for that. But I don't want to search over my metrics. I want to do different stuff with my metrics. Who is generally in agreement of that? Okay, a few, okay. That's fine. We've been working pretty hard to try to make it work for metrics as well. And I have a theory block to like show you all the things or efforts we have put into making it workable for metrics as well. And I also have a demo with an unreleased version, so let's hope that works. We'll see. So I work for Elastic, the company behind the entire stack. I mostly travel and speak about the stuff that we do and try to fix problems along the way. That's pretty much what I do. We have, if you have any questions, and you don't want to ask them in public, I can offer a Slido. So if you go to slido.do/my Twitter handle, you can post any questions there. And I will, if I have time at the end today, I will answer them here. If we don't have enough time, I will tweet out the answers afterwards. So if you go to slido/my Twitter handle, you can post any question there, and I will just answer them at the end if we have time. And otherwise, I will just tweet out the question with the answer afterwards. So even if you don't, because I don't understand Russian, unfortunately, if you don't feel comfortable asking anything in English, it's fine. You just write it there, and I will do my best to answer. Hopefully, that's easier for everybody. OK, so I generally want to break this into kind of like 3 blocks. We have like the building blocks, which is how do we do stuff to make it scalable. The architecture, what you need to do or how you can put stuff together to make it work. Then, also time dependent, a demo to see stuff in action and to show you some fancy new tools. Okay, building blocks. we have this development constitution, which is kind of an interesting document we have on GitHub that is kind of like the principles that we have for developing stuff. One of them, for example, which I find very interesting is if something is broken, we will remove it immediately, even if we don't have a replacement. And I know that a lot of people don't like that much, but we want to get rid of broken features early on. And another one is that we only accept features that scale. So we had pull requests in the past from the community for stuff that works fine on 3 nodes, but totally breaks on 50 nodes. And unfortunately, there is no way that we're going to merge that. So we are only adding features that do scale. And how do we scale in general? Well, horizontal scaling like pretty much everybody else, just to see how stuff works. So who's generally using Elasticsearch already? Just for a quick, okay, that's half or so. Just a quick recap of terminology and how stuff works in the background. Let's see how familiar everybody is with that. So yeah, generally the cluster is all the things working together on your queries. And the cluster is made out of 1 or more nodes. Here in my example, I have 3 nodes, for example. I have a node 1, node 2, node 3. And then you have an index. An index is kind of like related JSON documents that you put in a so-called index, and that index can then be split up into 1 or more shards. And one shard is actually a Lucene index, and that is what is being written to the disk. So there is no other data store behind it. Lucene is writing to disk, and Elasticsearch is kind of like the shell around it, which provides the REST API, the query DSL, and just talks to Lucene and makes it work in the background. So we have, let's assume we have one index here, and that index has 3 primary shards. Those are the things with the green lines around it. So you can see the primary shard 0, 1, and 2. And then every shard has 1 replica. So those are the gray boxes, basically. You see we have a replica 0, 1, and 2. And it's pretty evenly balanced. Every node has 2 shards. Primary and replica shards are not totally evenly balanced, but it doesn't really matter. Everybody has kind of similar amount of data. That is what we have in our cluster here. How do we even write a document then to make that scalable? So generally, whenever you do a request, either you do a single post or put, or you do a bulk request where you have multiple documents, that request will go to one node. We call that the coordinating node. And that node is basically taking your write operation and then looks at it. Is this a single write? Then it will figure out where does that data need to go. If it's multiple documents in a bulk request, we will figure out for every single document where it needs to go. How do we figure out where a document needs to go? Every document either has an ID that you assign it, then we use that ID. Otherwise, the coordinating node will generate a unique ID for that document. And then we hash that ID. Why do we hash the ID? Yeah, we hash it to evenly distribute the data, because otherwise if you had, for example, something like the email address of a user, it would not be very evenly distributed amongst the entire key space. But if you hash it, the assumption is you evenly distribute it throughout the entire key space. And then what we do is, since we have one index with 3 shards, we basically break up the entire key space into 3 even chunks. And through the hashing, all the documents, if you have plenty of documents, should then be evenly distributed amongst all the shards. So the coordinating node figures out, okay, there is the ID either provided by the client or generated by the coordinating node. It hashes it so it knows on which key space that ends. And then the master node, that is the one with the green star, keeps track of like which nodes are in the cluster, which indices do I have, and where are the shards of each index. And then it knows, based on the hashing of that ID, that document needs to go to that specific shard, like 0, 1, or 2, because the key space is evenly distributed. And then it knows, okay, the primary shard for that specific document is, let's assume, P0. So that ends up on that node here. So to make this practical, let's assume this one here is the coordinating node. This node figures out, okay, that document needs to be written to the primary shard, and then forwards that write operation to the primary shard. And then the primary shard says, like, yes, I can apply that write. And also, I know that there is a replica shard of myself. And I need to replicate that document here. So it replicates that document to the node 2 then. Then it waits for the acknowledgement from the node 2 that it has been written. Once the primary shard has received the acknowledgement from the 0 to n replicas that you have configured, Then it will go back to the coordinating node, which in this case is this one again, and tell the coordinating node, well, I have applied my write operation. Now you can acknowledge the entire write operation back to the client. And then you basically acknowledge that back. That's how we do one write operation. If you have a bulk, the coordinating node would break out every single document and would distribute that to the right nodes in the cluster. So basically, coordinating node to the primary shard to all the replica shards. They acknowledge back, you acknowledge back to the coordinating node, and then you acknowledge back to the client. That's how you do one write. If you do a get or an aggregate operation, once again, every read operation goes again to a coordinating node. Your client doesn't need to figure out where a document lives. So basically, if you do a get by ID, you send that to the coordinating node. The coordinating node will hash that ID again and will figure out, oh, it's that shard. Then you forward that request to the right shard. The shard will give the coordinating node the document back and hand that back to the client. If you do an aggregate where you aggregate lots of things together, the coordinating node will figure out these are all the relevant shards that have sub-results, and then it queries every shard. Give me your sub-results. For example, if you do the sum of how much network traffic you have received. And it knows like all the shards, it doesn't matter if primary or replica, it just needs to hit one of the shards. Give me back your sub-results. The coordinating node will combine the sub-results to the final result and will hand that out to the client. And then if you do the search, like in the full text search, once again, the search operation hits the coordinating node. The coordinating node will then figure out, okay, these are all the shards involved in my search operation. It will then send out that search to all the involved shards. That one will figure out which are the best documents, and then we have a two-step phase, but it doesn't really matter for today that much, how to actually retrieve the best matching documents. By default, you would get back the top 10 documents if you do a search. And it's always like coordinating node that distributes the work in your cluster and then hands back the sub-result or the result and does that to your client. So that's how you scale reads and writes. And obviously, if you need to scale up your writes, you want to have more primary shards so you can spread your load over more nodes. If you want to scale up your reads, you can add more replicas because either the primary or any replica can answer any read operation. So by scaling up the replicas, you have more nodes which can answer your queries. And what we don't do, by the way, is we do not allocate replicas on the same node as the primary shard, which probably makes sense because if the node goes down, it would go down with all the data. You just duplicate the disk space and you're not gaining anything. So we don't allocate any replicas on a node. If you have like a log or a metrics use case, you never update a document where we have one kind of nice optimization. Every time you do an update, what you need to do is basically, or if you do a write with an ID, so you know there is potentially a document with that ID could already exist, you need to check, does the document exist? If yes, replace it. If no, just create it. If we have this append-only situation where we're sending logs or metrics, where we never have an ID and the coordinating node is always generating those IDs, we never have to check for that update. That's why the purely write operation is a bit faster than any update scenario. We're doing that in the background. Another thing you might have stumbled into is that we have this refresh interval. So as already said, we have Apache Lucene doing the writes. And what Lucene does is basically it batches together all the writes of the past second into one so-called Lucene segment. And that's what it's being written to disk afterwards. And that segment is also an immutable data structure. So every time you update something, you mark the old document as deleted and replace it with a new write operation in a new segment. And by default, that refresh interval is 1 second. You can turn it up, for example, to 5 seconds. Then it might take up to 5 seconds until your documents will be found afterwards. But it will allow Lucene to create larger segments while writing, like approximately 5 times as large, which is good because afterwards, if you have a lot of small segments, at some later point, we will merge them into larger segments together. And that merge operation is obviously pretty heavy, both in terms of memory, but also in I/O. So if you can turn up the refresh interval to create fewer but larger segments, that will increase your throughput. However, it will take slightly longer until you can find something. But oftentimes, maybe you can tolerate a 5-second delay, and that's fine. In the next major version, in 7, we actually have a more clever approach for that, where we know that you haven't done any searches for that data recently. So we don't really create those segments right now, because obviously you're not reading them on a very frequent basis. We just create larger and larger segments, And as soon as you do a search operation, we will then do an explicit refresh. But it's basically figuring out in the background, like, hey, I don't need to refresh that often. I can create those larger segments automatically. But as soon as you do a read operation, we will force that refresh, and you will get your fresh data back sooner. That is another nice operation that should, especially for that write-only use case where you don't read that often, should improve your performance by quite a bit. Storage compression, we have LZ4 by default. You could switch to deflate for an index level. And the nice thing is you can change that for an existing index, and all the new segments that you're writing will be written with the new compression level. So you can increase the refresh rate. And if you do a force merge, where you merge segments together, since they're rewritten, you could change the compression rate later on as well on data. And then we have something, we don't really store like integers or longs anymore. We have so-called BKD trees, which is a very fancy data structure, which is for multi-dimensional points. But luckily, integers are also like one-dimensional points. And here's, for example, the comparison. If you have like that BKD structure, it's just more compact and is faster to operate on than the classical int field, which we had before. So this is one optimization that we have put into place for that. Another thing that we have is half and scaled floats. So oftentimes you have float values, but oftentimes you also don't need the full precision of float values. Because, for example, if you have the system load, which is normally 0. some number or 1 some number, depending on how many cores you have, you don't really need the full precision of floats. What we can do for that is basically we have half floats, which give you for half the disk space, half the precision, and scaled floats, where you can provide a scaling factor, which looks something like this. So here we have taken, I think this is 10 million random float values that we have inserted, and you can see disk uses and memory usage for the heap. We've combined those. For float is approximately whatever. Half floats is approximately half, and then scaled floats go down. So what you store by, on scaled floats with a factor of 100, for example, you store an integer value. But to get back the original value, you have to divide it by 100. So you basically have 2 digits after the comma. But your precision is, of course, limited by that. The nice thing about the scaled float with a scaling factor of 4000 is that it gives you the same precision as half float. So the scaled float factor of 4000 is slightly more compressed than half floats. That's why we're never, or why we generally don't use half floats anywhere really. And for example, if you look in the into the configuration of when we collect the system load, you can see we're using a scaling factor of 100. So you have the system load, which is, assume you have 2 cores, and then it might be 1.50 or whatever to store the system load. We define the scaling factor of 100 and then store that scaled float. And then you have the load average for the last minute, the last 5 minutes, whatever. And we store data like that. Is anybody aware of the all field? We used to have the all field, which was very convenient. Basically, every single field that you had in a document, we would also put into a magic field called _all, which is nice because you don't need to think like, in which field do I want to search? I can search across everything. Kibana was doing that a lot, because in Kibana you have this search box, and there you could just enter whatever and it would search everything. The downside is, basically you duplicate all the data you have into that _all field. And we don't do that anymore. We stopped that because it was just like increasing the storage size by 30% or something like that. And we removed that. You can either do that explicitly, or you can just say search across all these fields that I provide, and Kibana is doing that automatically for you as well. So this is another thing where we saved quite a bit of disk space. Since Elasticsearch is written in Java, heap is always an issue, especially if you once you hit the memory or garbage collection, the larger the heap, the longer the garbage collection will take. And we're trying to get off, or as much data off the heap as possible. So we had field data which was in the heap for any numeric value. By now the numeric values are not stored in the heap anymore, but we have a new data structure called doc values, and that is off heap. And that will be explicitly garbage collected around it, but it's not part of the heap, and it will not make your garbage collections longer to make that easier. Okay. Those are kind of the building blocks. Let's see how we can dive into the architecture. A very common pattern for us is that we write time-based indices. So you have some metrics today. We always add the version. So if we have a breaking change, we have a new index with a new version, and we don't have any collisions around that. And then we oftentimes have like a day. This would be the default pattern where you have like year, month, day. So every day you collect some metrics, you would create a new index. And tomorrow you would create another index where you put your data in. That is kind of simple because, well, only today's index will be written, and yesterday's and past indices will only be read. And it's also very easy to reason about that, well, this index is that large. Anybody knows what is the number of shards we allocate by default? Yes, it's 5. So if you don't have a lot of data, you will create a new index every day with 5 shards, plus 5 replicas. So in total, in the default settings, you would have 10 shards for every single day. The problem is, if you don't have a lot of data, all the shards have kind of some overhead. So you will, kind of like your cluster, will have to keep up a lot of resources just for the number of shards. Does anybody have an idea how large a shard should be approximately? Which is also a very common question. Sorry? 32? Yeah, it doesn't have to be a power of 2. It's a bit dependent on the use case. Normally, for search use cases where you have like all the data is hot, it's a bit smaller, where we would say a shard should be around 10 gigs or so. And then for logs and metrics, it can be larger. So we sometimes say like up to 50 gigs. But it should definitely be in the gigabyte range. What we often see is that people have this pattern, and then they have like the 5 primary and 5 replica shards per day, but then they only have like 100 megabytes of data per day. And then you basically waste a lot of resources in terms of memory, but also file handles, just for the number of shards. So this is kind of a problem. The next problem is, let's assume we have a service that runs, like, say, five instances all the time. But it might scale up to 25 during the week when you have like peak load. So it might have suddenly 5 times as much metrics to collect because you have 5 times as many services. The problem is that your shard size is then very unevenly distributed, because with that pattern, every day we'll have the same number of shards, which might not be great if you have spiky loads where you have, for example, very few visitors on the weekend and a lot of visitors during the week. Anybody knows what a way around that might be? Sorry? Postponing, yeah, but since it's state-based, you cannot really postpone it. What we have instead is we have so-called rollover indices, where we basically say you can define a condition when you want to actually create a new index, which might look something like this. So here I'm creating the beat 0, like lots of zeros, 1, I think it's 6 digits always. So you have the 0001 as the first one, and then you basically define a condition, and when that condition is met, that index will be rolled over to 00002 at that point. And the condition could be, as soon as you hit one of these 3 possible conditions, so you can say either once that index is a day old, once it has hit 1,000 documents, or it has 5 gigabytes in size. If you do lots of inserts, this will probably hit the 1,000 documents first. And then it will basically acknowledge back and say like, hey, yes, the old index was 0001. That one reached the limit. We rolled over because, well, it hit the 1,000 documents. We have created a new index now, 0002. Now you can do your write operations there, and later on you can apply that rollover again. And then all your indices will have either the same number of documents, the same age, or the same size, depending on which condition you define. And then your indices will be very evenly sized, and you don't have that problem with weekdays and weekends anymore. Another thing that we have recently added are rollups, which are very fancy. So rollups, the idea is, for metrics, doesn't apply for logs, obviously. Today, for example, you have 10-second intervals. But in a week, you might only care about 1-minute intervals. And in a few weeks, you might only care about like 1-hour intervals, to basically thin out your data and aggregate together what data can be aggregated together. So yes, think about the bytes. What it basically looks like is you have a condition that looks something like this, if the screen switches. So, and this is unfortunately super small. Since this is all text, let me switch over to my editor. Oh no, this is the wrong window, sorry. So I hope this is more readable. So basically what I'm saying here is it more readable for everybody? On this index, I want to roll up the data from this index into this other index. I want to run a cron job like every minute and page together up to 1,000 documents. And basically, I want to have a date histogram of 5-minute batches. So whatever size intervals you had, what I'm saying here is after 5 minutes delay, I'm putting together 5 minutes. So this is only for the demo use case here, because normally you would want to keep your short intervals for a few days probably. But for the demo here, I'm saying like after 5 minutes, I want to group my 10-second data, which you don't see here, but that's the way I write it. I want to aggregate that together into 5-minute intervals. And I want to keep that broken up on the container because, well, I have multiple containers running here. And I want to have that for specific fields. You need to define every field and every aggregation you want to do on that. So the fields I'm interested in here, for example, is the network traffic in and out of the container. And I'm only interested in the sum. We can do the same thing in a more graphical way. And here you can, for example, see we have 3 different attributes, and you can define minimum, maximum, average, sum, the value count, and the cardinality. Those are basically the aggregations you can do on every time slice. And then we aggregate that together, and obviously that will use a lot less disk space than the original metrics, depending on how large the chunks are that you aggregate together. The next thing that you want on the architecture side is that you want to have different node sizes. We normally call them hot, warm, cold. Especially if you have like this daily index pattern or the rollover index pattern. Let's assume for simplicity, we have the daily index pattern. So today's index is where you do all your write operations. So you probably want to have fast disk to do all the write operations. Yesterday's index is read-only because we're not adding any metrics to yesterday's data anymore. Then you might have some slower data or some slower nodes already or higher density on the node. And then you might say I have like cold nodes which might be older than a week because commonly you maybe just want to have metrics for today or the last 3 days or something like that. In rare cases, you might want to be able to go back like more than a week, but it's kind of rare and you're willing to wait a little longer for that. But you are also don't want to spend too much money on that. So you might have the fastest nodes for the hot indices today. The warms have like medium-sized hardware, and then the cold nodes have like the slower hardware, like you have spinning disks just to keep the cost down. And you have like a 3-tiered architecture. And what you do is basically, when you start an Elasticsearch node, that's the first 3 lines, you can say, this is a hot node. And then when you create an index, you can say, I want to write this index to a hot node. And then that index needs to be stored on a node that has this attribute hot. And once the data is, you are finished writing and you're kind of tomorrow, and you know you're not writing anything anymore, then you could change that setting to go to the warm index. That index to the warm node, and then you have another node with the node attribute size warm, and then Elasticsearch would automatically move the data over to the other nodes for you. And that will happen in the background automatically. And at some point you could move it to cold nodes as well. We also can search across clusters, so if you have like geographic distribution, one Elasticsearch cluster should always only be in one geographic region, because I showed the primary and the replica, they always need to acknowledge back. And if you have that with a lot of latency in between, it might make your cluster slow and unstable. So one cluster should always be in one geographic region. But if you're like Blizzard, a big gaming company, you have users everywhere. And you probably want to have local clusters to make write operations faster. What you can do is we have this thing called cross-cluster search, where you basically search across multiple clusters. So you have one cluster in Europe, one in Asia, and one in the US. But you still want to get your metrics across all of them. And then you can just search all of them, and Elasticsearch will do that in the background and search the other clusters as well. We soon will also have the ability to replicate the data from one cluster to another cluster. That is like the standby cluster, where you can say, okay, in one geographic region I have this cluster, but I also want to, if that entire data center goes down, I also want to replicate that data to another continent or to another data center. It's too far to be one cluster, but I want to have this possibility to replicate the data over. That's something you can do as well. Okay, now we have like 10 minutes or so. Let's see how this is going. So let me start my setup. So I try not to cheat and I'll show you what we actually have here. So I'm using Docker Compose to keep it simple. Basically, I have one Elasticsearch node which is hot. And then, yeah, I give it 1 gig of memory and half a gig of heap. And here I have this setting that this is a hot node. Then I have the same thing for a warm node. And then I have the same thing for a cold node. And then we have one Kibana instance that talks to the hot node, just because we assume we do most of the queries there, to talk to that. And then we have a metric beat, which collects metrics. And my metric beat is collecting system and Docker metrics. And then I have a short-lived container, which is basically doing some setup for me in the background as well. But that's pretty much it. So what metric beat is doing, basically, I want to collect any Docker metadata. And I have my Docker module where I basically collect these pieces of information from every Docker container that I have running, plus some system metrics like how my system's doing. What I'm doing here is, what kind of index pattern do I have here? A minute-based one, which is a really bad idea. Never do that in production or anywhere, because this will create a new index every minute. But it's just for the demo purpose, because otherwise you don't probably want to sit around with me until tomorrow to see that we create another index. That's why we create one index per minute. And also every index has 3 shards. I have set the replicas to 0, because all that data should go to the hot node and I only have a single hot node. Otherwise the replica would never be allocated. I could set it to 1, but then my cluster state would be yellow because it cannot allocate all the replicas. But yeah, so. And while I've been talking, I hope that, okay, my cluster is still starting up. So I have my 3 Elasticsearch nodes, metric beat to collect the metrics, Kibana to show you what is going on, and then the short-lived container to actually set that entire thing up. And it hopefully will not take more than another 30 seconds or so until all of them are up. Just to quickly show you. This is unfortunately very hard to read. Let's see. Yeah, it's still too large. Okay, I hope this is, no, this is not readable. But you should, in theory, you would see that we have the 3 nodes that we've been talking about here, the Elasticsearch nodes, and they are hot, cold, and warm, and we can talk to them. And hopefully, the hot node has created an index pattern, so I hope that it's about ready. So let's see. Let's see if Kibana is up and running already. No, I don't want to send any statistics. Otherwise, I'm faking all the statistics. So you can see this is the latest version of Kibana. This is an unreleased version, but hopefully it will be out soon. We have added some more features just to show you what we have here. And you know, with demos, I'm always praying that everything works. This is not what I want. What is my... I think my nodes are still kind of starting up because we need metric beat, Docker logs. Uh-oh, did I just screw up my configuration? That would be unfortunate. Gold. That is not going to help. Oh no, I deleted the wrong file. Restore, restore, restore. This happens when you break demos right before you do them. Let's see, did you recover? This is unfortunate, let's see. DevTools. let's see what we even have in our cluster here. So generally, let's fold that in to make it slightly larger so you can see a bit more. So we have a 6.5, which is unreleased cluster that should be working. Let's see which indices we have. And okay, it kind of recovered because we just started inserting 2 indices with metric beats. So it just took a little longer to start up. Let's see what infrastructure-wise is running here. So we have one host which is running our metric beat, but on the container side, you should see more. So you can see on the container side, we have cold, hot, warm, Kibana, and metric beat. So those are the 3 containers we have, and then you could sort them or drill down. Right now I'm looking at CPU. We could also say like, okay, how do they look memory-wise? Because yeah, the Elasticsearch instances need more heap. We can also look into the raw metrics. We have a dashboard that's a pre-built dashboard. I'm lazy, I didn't build that myself. But there is a Docker dashboard for the metrics. And since the entire cluster is just starting up, it's just figuring out how much data it has because we don't have 15 minutes of data yet. But you can see, okay, these are all my instances that we have running here. We have 5 containers in total. 1 has been stopped. That was the short-lived one that set up the entire cluster. You could, for example, see here, if I make that full size, which containers I have and what they're running. So here we have 3 nodes running on the Elasticsearch base image. That makes sense because we have the cold, the warm, and the hot node on that. And then we have metric beat and Kibana running here as well. And here you can then see how are they doing CPU, memory, and network-wise. And since I just started them up, we don't have much historic data, but we get kind of some data here. The other thing that I find very nice to show off is we have now these roll-up jobs, so you can configure that visually. So here, for example, we say I want to have a job called I want to roll up my metric beats. And the index pattern from where I'm getting my data is metric beat. So just to head over to show you which index patterns we have in total. Basically what I have is I have these indices here. You can see we're getting a new metric beat index every minute. And we can then see where the shards are being allocated. And yeah, I broke the setting because, well, right now they're all over. They should all go to warm, but we can fix it, the setting afterwards. So we have all these shards, and what I want to do is I want to roll up the data now. And let's say we call it metric beat roll up, where the data should go. By the way, what you cannot do is, and what you shouldn't do is, this name needs to be disjunct from this. So if I call this metric beat dash, it obviously wouldn't work because it would be recursive. Because that index pattern would then match that one and would try to roll up into itself. So I'll just follow the pattern to use an underscore here and here dash star. So they're disjunct. Then you can say, I want to run this job every minute for up to 1,000 documents, and I want to aggregate 5 minutes together. Hopefully I'm talking long enough that we get 5 minutes. I have a timestamp, and this is what I want to aggregate on. And I want to bucket together, let's say, 5 minutes always. Could be 3 minutes or so, or let's say 3 minutes to have some distinction here. Times are always UTC. I want to add a term so on which I can break that up. Docker. For example, we could say the Docker, let's say we break up on the container ID. Oops, that was too much. Container name is not what I want. So we create the aggregation not for everything together, but per Docker host, because it's the container ID that I'm using. It could also be the container name if that was unique, but let's go for the container ID. I don't want to add any specific histograms, but I need to add the metrics I want to add. So the metrics I'm interested in is Docker network. Let's say the in bytes and the out bytes. And for those, we want to have, let's say we only want to have the sum, that we sum together just the network traffic ingoing and outgoing. Then you can review that, and if I did everything correctly, it will allow me to save. You can, by the way, see the entire job here, that is the JSON, and you could also just store the JSON and throw it against Elasticsearch rather than putting that together visually. You can see which feeds we have, on which terms we're aggregating, and, well, the summary. Let's see. Okay, that worked. It is disabled by default. I'm starting my job now. And depending on how much data we have by now, we have a roll-up already. And it has only one document. So this is the number of shards. This is the number of documents. And you can see we have very little data in there. Let's see what that looks like. So if I do a get metric bit roll up search. If you can type it correctly, it would help. It hasn't rolled up anything yet. Probably, do we have enough documents yet? Do we have 5 minutes already? Yes, 35, 41. So it should, hopefully any minute now, start aggregating something together if I put that together correctly. It started, okay. One processed, one triggered. Okay. In theory, this should start aggregating documents together now for us. But since we're running low on time, I'll fix that afterwards. Okay. So what is still upcoming, and that is hopefully coming early next year, is we'll have something called index lifecycle management, because right now, I don't know if anybody is running that, but we have Curator to actually clean up your data. What ILM, index lifecycle management, will basically replace Curator, which is like a standalone Python tool, and it will run as part of the Elasticsearch cluster. And what it looks like, for example, is here that you say we have this policy where we define the hot phase, and we say, for example, I want to use rollover here, and I say I want to have 3 gigabytes, and we will set up everything correctly for you. And then you can say after, right now I have 0 days, but probably that should be 5 days or 7 days or whatever. I want to have a warm phase. You can then say, so here you can say that when it should happen. You can say this needs to go to this other node type. You can change the number of replicas afterwards. You could shrink the number of shards down, and you could do the force merge, and you, for example, could change the compression on that. So that's kind of like all in one go to that warm phase together. And then you could have a cold phase where you could do something else, and then you could have the delete phase where you say after 30 days or whatever, I want to delete everything. Which is also interesting. Like normally when you ask people like, what is the retention you want? The business often says like a year, because that's the first number they can think of. And then you tell them, oh, a year will cost you amount X in hardware. And then oftentimes the answer is, okay, 30 days are also good. That's something we see kind of commonly. But for example, for metrics, with the rollups, it will get much cheaper to thin out the data over time. Obviously, logs cannot be rolled up, because one event is one event, and you cannot aggregate it together to anything else. That's not possible. And we will add one other thing that will help with the storage to heap ratio, which is called frozen indices, which is basically an index that is still searchable, so it's not closed, but it will be slowly searchable. So it limits the number of threads doing searches concurrently. But it basically will allow you to get much bigger or instances with much more storage, which you can then still search data through. So for example, if you say, oh, it's too expensive to keep data for more than 30 days, you could keep that on that frozen instance where it might be achievable to then keep like another 30 days, but it would be searchable a bit slower. Okay, to wrap up, we've seen like building blocks, the architecture, and a demo of like the new things that we have and how to put stuff together. The next question is, people always ask about benchmarks to show like this is so much better than any other system. The problem with benchmarks, normally you need to have them fair, reproducible, and kind of close to production. And that's already the problem, especially close to production, because very few people have the same scenario. And my favorite answer for, can you show me some benchmarks showing that this is so much faster than everybody else, is this one. I'm not sure how easy it is to read, but here the professor is benchmarking two systems against each other, the squid and the house cat, under similar conditions. And this is pretty much what you get whenever some vendor benchmarks their own product against their competition. They will always find some scenario that is great for themselves and not so great for the others. I remember like a few years ago, there was this benchmark where MongoDB, Cassandra, and Couchbase were all benchmarking their products against the other two. And everybody found a scenario where they were at least twice as fast as their competitors. And that's pretty much what you need to think about whenever you see some benchmarks with others. You can totally benchmark your own scenario for yourself because you know what your scenario is and what makes sense for you. That is valid, but don't trust in any vendor benchmarks. That's why we don't publish any benchmarks, because you would always kind of like have weird benchmarks where you know your system will be better, or also because you know how to tweak your system, and you don't know how to tweak the other systems. So you will often come out better even if you don't really want to. So don't do that. Yes, but as a vendor, I cannot provide independent benchmarks. And then the problem is the scenario the same for or is the scenario close to the scenario that you actually have in production? Because if you test a different scenario, it can be like, what is your read-write ratio? How much data do you actually have? There's so many factors that play into that and change your benchmarks a lot that there is no good answer, or there is no final answer to that. It's like, for this specific scenario with these parameters, you can do a comparison, but you cannot say like, oh, I ran one benchmark and product X is faster than product Y. Doesn't really work like that. Generally, our idea is, since we have logs, we also want to add the metrics, because we don't want to have like little islands for one log island and one metric island and one tracing island. We try to kind of have this more global map. That's kind of the general idea of our stack. And with that, do we have any questions? Yes, please. Yes, we would need a microphone, please.
Hi, my name is Ilya.
Hi.
Thank you for such nice explanation. You mentioned some cool features. Are they all open source?
So what I have shown you is 90% open source. The one thing that is not open source is that UI that I've shown you to create the rollup. So that is free, but not open source. Why is it free and not open source? Because you can get Elasticsearch and Kibana from AWS, for example, which are not nice to us, and you can't get that on AWS. So we have our own cloud service, and this is free when you run it yourself, and it's included in our cloud service, but competing cloud services cannot get some features. Like, we have some nice add-ons on top that are not available on other cloud providers. So if you go to competitors of ours, that's our advantage, but this is free to use. The API, I think the API is open source. It's just the visualization that is not open source.
Thank you.
I hope. I'm never sure about licenses. But it's generally a free feature that you can use. Just don't use Elasticsearch on AWS.
Hi,
Hey.
Thanks for the talk. You showed this roll-ups. Is there any nice integration for the UI? Because the roll-ups then like have another granularity, and you showed that you have different things, so it only works when you really have then in Grafana all roll-ups from, if you look over 3 months, integrated with the hot phase. So is this kind of nicely out of the box there? Or?
Yes, the visualizations, depending on, so I cannot just take the general dashboard if I don't have all the metrics, but for example, for the network in and network out, if I want to make a visualization, it could then use both the thinned out data and the current data. But of course, you would have a lower granularity on the thinned out data. But if you want to show the sum of the network transfer, I mean, we will automatically, if you say like, give me a week of network traffic from my container, we will not give you any single data point anyway. We would sum that up and bucket it automatically into 1 hour slots, basically. I would assume something like 1 hour, for example. And if you have like 5 minute or 1 hour granularity in the rollup, you can just use that in the general visualization as well. So that's the explicit goal, that your visualizations don't totally break. Obviously, the old data will be thinner and you cannot zoom in that much. But the general idea is that dashboards keep working and the visualizations keep working with that.
Okay, yeah, thanks for your presentation. And I have a question about functions that you, because in roll-up jobs, I can understand the meaning of this thing in general, but I don't agree that average for metrics is very useful because usually we want to see some percentiles, and I can't see in current implementation any functions that will help us because it's not useful to just sum up and divide by some numbers. You will get something not that useful, I would say. So.
Yes, I mean we have the minimum and the maximum as well, so you can include that. My mathematical model is fuzzy. Can you even do percentiles on aggregated data?
I mean, you just...
Probably not, so that's why we don't have the feature.
You just need to exclude some outliers to sum up and have something useful. For example, we want just have each 5 minutes 99, for example.
I don't think percentiles work like that.
I mean, how you get your average. For 5 minutes interval, you just sum up each and every value, then just divide by the number of, and that's how you get your average and just store it.
Yes, but you can do the average over 2 or 3 of those then, but what is the, but if you don't have the...
Yeah, that's, okay.
Yeah, not all the mathematical functions are available on that aggregated data. That's kind of the trade-off. We might be able to do some tricks in the future, but I'm not sure. We'll see. Okay, I'm afraid we are out of questions. Just come to me afterwards. Also, I have a couple of stickers up there. If you want stickers, just grab them. Thanks a lot.